Welcome to This Explainer. Have you ever actually stopped to wonder why some buildings stand tall for centuries while others crack, tilt, or just completely sink? The secret isn't in the steel or the concrete. It's right there in the ground beneath our feet. Think of the Leaning Tower of Pisa. It's a world-famous architectural blunder caused entirely by a misunderstanding of what was underneath it. So today, we're demystifying that hidden world of soil. We're shifting our perspective from seeing simple dirt to understanding a highly complex, dynamic engineering system. Because it turns out, the earth you stand on is a fascinating structure, and truly understanding its composition is absolutely crucial to safely building the modern world. All right, let's look at our roadmap for today. We'll be covering the hidden nature of soil, the three-phase system, when soil phases disappear, speaking the engineer's language, and finally, connecting the soil dots. Let's jump right into Section 1, the hidden nature of soil. So, what exactly is the ground beneath your feet? It sounds like a wildly simple question, right? We walk on it, we pave over it, we plant gardens in it, and we generally barely give it a second thought. But the answer actually changes drastically depending on who you ask. And getting that answer wrong when you're constructing a building, well, that can literally cost millions of dollars. If you ask an agricultural scientist, they look at dirt and see life. They want that loose, organic material full of nutrients on the Earth's crust to support roots and grow food. But a civil engineer? They view it through a completely different, almost opposite lens. To an engineer, soil is a structural material. It's that crucial, unconsolidated, inorganic layer sitting just above the hard bedrock that absolutely must be able to support thousands of tons of steel, glass, and concrete without buckling. If it's too loose or too organic, it's an absolute engineering nightmare. Our source material actually offers a really fascinating definition, calling soil a complex physical system, a more or less random accumulation of soil particles, water, and air-filled spaces. Think of it kind of like a giant underground kitchen sponge. The solid part of the sponge is just one piece of this massive puzzle. What really dictates how the ground behaves when you build a house on top of it is whether those microscopic holes, the voids, are filled with squishy, compressible air or heavy, uncompressible water. Moving right along to Section 2, the three-phase system. So here's the core problem we run into. Real-world dirt, it's chaotic. It's this messy clump of irregular grains and random pores, and you just cannot easily plug chaos into an engineering formula. So engineers use a sort of conceptual X-ray vision. They abstract that messy real-world clump into clean, perfectly separated rectangular blocks of air, water, and solids. This mathematical lifesaver is called a phase diagram, and it basically takes the unpredictability of nature and turns it into clean geometry. Because this underground mass naturally contains material in all three states of matter at the exact same time, you've got solid grains, liquid water, and gaseous air, it is officially classified as a three-phase system. This is the bedrock model of all geotechnical engineering. By separating the chaos into these three distinct, highly measurable phases, engineers can start to predict exactly how a patch of earth will compress, shift, or settle when, say, a heavy bulldozer rolls over it. Which brings us to Section 3, when soil phases disappear. Now, nature is notoriously dynamic, right? So this delicate balance of three phases isn't always permanent. When extreme environmental conditions hit, that complex three-phase system can actually lose a phase entirely, simplifying into a two-phase system. The rules of the engineering game completely change depending on the weather and the environment. What was once a balanced mix of air, water, and solid can literally transform overnight. So how does a phase just disappear? Well, imagine a massive flood. All the voids in our soil sponge fill completely with water, pushing every single drop of air out to the surface. It becomes a fully saturated two-phase system made only of solid and water. On the flip side, in an extreme drought, the water evaporates, leaving a completely dry two-phase system of solid and air. But here is a highly surprising fact. True, absolute dryness is incredibly rare in nature. Unless you literally bake a chunk of dirt in a laboratory oven at high temperatures, there is almost always a microscopic layer of moisture stubbornly clinging to those solid soil grains. All right, Section 4, speaking the engineer's language. Let's dive into the composition of soil terminology and definitions. We're going to rapid fire through 5 key terms that make up the engineer's alphabet: porosity, void ratio, percentage air voids, air content, and moisture content. As we go through these, keep one golden rule in mind. The word voids simply refers to the empty holes in our soil sponge.
Mastering this specific vocabulary is the absolute only way to truly decode geotechnical engineering and understand how the composition of soil actually works.
First up is porosity, represented by the letter N. Porosity gives us the big picture. It tells us exactly how much of our total chunk of ground is actually just empty space. It's calculated as the ratio of the volume of voids to the total volume of the soil mass. Think of a block of Swiss cheese. Porosity basically tells you how much of that cheese is actually just holes instead of dairy.
Next is void ratio, represented by E. Now, instead of looking at the total volume, this directly compares the amount of empty space to the amount of solid, indestructible dirt particles. You might be wondering, why do we need this if we already have porosity? Well, if you put a heavy weight on soil, the total volume shrinks as the air is squeezed out, but the volume of the solid grains never, ever changes. So void ratio anchors our math to the one thing in the ground that is an absolute constant.
Then we have air content, or AC. This metric zooms in strictly on the holes themselves, ignoring the solid grains completely. It measures what percentage of that void space is filled specifically with air rather than water, and this matters immensely, because air compresses almost instantly under pressure, while water doesn't. Knowing your air content tells you exactly how squishy the ground will be immediately after you build a structure on it.
Finally, water content, denoted by a lowercase w. The crucial mental shift here is that we are no longer looking at volume, we are looking at weight. It's the ratio of the weight of the water to the dry weight of the solid grains. Water is incredibly heavy. A hillside with low water content might be perfectly stable for decades, but if heavy rains drastically increase the water content, that massive added weight can instantly trigger a catastrophic landslide.
And finally, Section 5, connecting the soil dots. So, how do engineers solve massive, real-world problems without getting bogged down in impossible calculations? They use a clever mathematical cheat code called the unit phase diagram. Instead of dealing with millions of cubic yards of real-world dirt, they construct a theoretical model where they set the volume of the solids to exactly 1. Because our void ratio E is just the volume of voids compared to the volume of solids, if solids equal 1, then the volume of a voids is simply E. It literally turns a chaotic algebra nightmare into simple, elegant arithmetic. By stepping through the logic using this new unit phase trick, a complex derivation becomes just a simple combination of our basic terms. By substituting these theoretical weights and volumes, engineers easily derive beautiful, highly reliable equations. It proves that all these properties, water content, specific gravity, saturation, and void ratio, interconnect flawlessly. If you can measure just a few of these numbers out in the field, the math effortlessly reveals all the rest. So we've got the terminology down. We've broken this chaotic, muddy world into a neat, highly measurable three-phase system. But that leaves us with one massive, high-stakes final question. What actually happens to that delicate balance of air, water, and solid when we drop a 50,000-ton skyscraper on top of it? How does that crushing, relentless weight physically squeeze the water out of those microscopic voids over decades, potentially causing the building to slowly sink into the earth? That is the true challenge of geotechnical engineering. It's a delicate, ongoing balancing act happening right beneath your feet, and it's for sure something to think about the next time you look up at a towering city skyline.